Okay, we're gonna explore a little bit this relationship between light travel time and time. So when sunlight enters your eyes, that light is a bit over 8 minutes old. When I'm looking at my hand at arm's length, it's about a meter away. So it's a fraction of a nanosecond in the past. So every time you see light from an object, you are in fact seeing the way that object looked in the past. And the further away the object is, the further in the past you're seeing it. That is not something that you notice in everyday life. My hand or my wall are essentially the same distance away from me in terms of light travel time, at least as far as I can perceive it. But in astronomy, that's very, very different because space is very big and things can be very, very far away. All right, so let's try this little exercise. So imagine you have received 6 pictures of 6 different children who live near 6 of the closest stars to the sun. Each picture shows a child on his or her 12th birthday. The pictures were each broadcast directly to you using a satellite on the day of the child's birthday. And note that the abbreviation LY is used below to represent a light year. So Melissa lives on a planet orbiting Ross 154, and that is 9.5 light years from the sun. Max lives on a planet orbiting Bernard star, which is 6 light years from the sun. Jade lives on a planet orbiting Sirius, which is 8.6 light years from the sun. Sydney lives on a planet orbiting Alpha Centauri, which is 4.3 light years from the sun. Joyce lives on a planet orbiting Epsilon Eridani, which is 10.8 light years from the sun. And lastly, we have Crystal, lives on a planet orbiting Procyon, which is 11.4 light years from the sun. All right, describe in detail what a light year is. Is it an interval of time, a measure of length, or an indication of speed? And it can be only one of these quantities. So a light year is the distance light travels in 1 year's time. So it is a distance or length. And this causes all sorts of confusion. But a light year, even though it has the word year in it, a light year is a distance. And that is sort of a convenient measure of distance because then it naturally tells us something about time. If I know that there is an object in space that is a light year away, then I'm always seeing what it looked like a year in the past because the light took a year to travel from there to here. All right, let's go to question 2. Which child lives closest to the sun, and how far away does he or she live? Well, I sort of remember some of these stars, and I know out of that list, Alpha Centauri is the closest. And in fact, yes, there it is, 4.3 light years is the smallest of allest. And Alpha Centauri is the home star for Sydney. And 4.3 light years away. What was the greatest amount of time it took for any one of the pictures to travel from the child to you? Well, so that is then asking what is the greatest distance out of these, and that is for Procyon. 11.4 is tallest of allest. Yep, so there we go. So what was the greatest amount of time? 11.4 years. If each child was 12 years old when he or she sent his or her picture to you, how old was each of the children when you received their picture? So we'll just go through. Melissa is 9.5 light years away, and so her age is going to be 12. When I receive the picture, her age is going to be 12 plus 9.5 years for the light travel time. So 21.5 years old. Sydney, 4.3 light years away from the sun, so 12 plus 4.3 years is going to give me 16.3 years. Max, 6 light years away, so 12 years plus 6 years for the light travel time. It's going to be 18 years old when I received Max's picture. Joyce, for Epsilon Eridani, 10.8 light years from the sun, 10.8 plus 12 is going to give me 22.8 years old when I get her 12-year-old picture. Jade is orbiting Sirius, 8.6 light years away, so 12 plus 8.6 is going to be 20.6 years old when I get their 12-year-old picture. And then lastly, Crystal. And Crystal is there for Procyon. This is our furthest away. So 12 years old plus 11.4 years for the signal for their picture to reach me. So 12 plus 11.4, 23.4 years old. All right. Is there a relationship between the actual age of each child when you receive their picture and his or her distance away from Earth? If so, describe this relationship. Well, there is, so we're just using it. And what would that be? 12 years plus the light travel time. Okay. And then what's the light travel time? Well, if it's 11.4 light years away, it takes light 11.4 years to travel. All right, question 6. Imagine that the 6 pictures were broadcast by satellite to you and that they all arrived at exactly the same time. For this to be true, does that mean that all of the children sent their pictures at the same time? That couldn't work, because they're all different distances away and different light travel times. So if not, which child sent his or her picture first and which child sent his or her picture last? So for the pictures to all arrive to me at the same time, the one that's furthest away had to send it first. So furthest sent first, and the furthest away was Crystal. And then for this to work out, who sent the picture last? The closest child. And closest is Sydney, because they're on Alpha Centauri. Well, planet around Alpha Centauri. Pretty rough to be on Alpha Centauri. A little warm. All right. So now, instead of talking about children and pictures from when they were 12 years old, let's talk about light from other objects like galaxies and stars. So more astronomical in nature. All right, so I have a telescope image at the right. It's taken of the Andromeda galaxy. It's our closest neighboring galaxy, at least big one. It was located about 2.5 million light years away from us. Is this an image showing how Andromeda looks right now, how it looked in the past, or how it will look in the future? Explain your reasoning. Well, this is what Andromeda looked like in the past. The light needs to travel for 2.5 million years to reach us. So this is how Andromeda looked 2.5 million years in the past. I don't know what it looks like now because the light from now is going to take 2.5 million years to reach my eyes. So everything that we see in space, we're always seeing the way it looked in the past. All right. Imagine that you're observing the light from a distant star that was located in a galaxy 100 million light years away from you. By analysis of the starlight received, you are able to tell that the image we see is of a 10 million year old star. You're also able to predict that the star will have a total lifetime of 50 million years, at which point it will end in a catastrophic supernova. That's what your book is going to refer to as a massive star supernova. All right. So how old does a star appear to be to us here on Earth? Well, it looks like it's 10 million years old. How long will it be before we receive the light from the supernova event? Well, it has 40 million years of its life to go, so we will see that we're seeing it as it looks 10 million years old now, so we will see how it looks when it's 50 million years old, 40 million years in the future. Okay, and then this galaxy is 100 million light years away. So has a supernova already occurred? Yes. This star has lived its entire life and exploded as a supernova before the first light that the star existed reached us. All right, so when did it occur? Well, we have to wait for 40 million years, so that means it already happened 60 million years ago. Okay, that always bends people's noodles. There are, well, not all stars have lifetimes this short, but also not all galaxies are this close. 100 million light years away is actually not that far. But definitely things that exist in the sky that we are just seeing the light for them now, and they actually no longer exist, quote unquote, now. All right, question 9. Imagine that you take images of two main sequence stars that have the same mass. So what those words mean, main sequence star is a star that is fusing hydrogen to helium in its core. That's the stage of life that lasts the longest for stars. So imagine that you take images of two main sequence stars that have the same mass. From your observations, both stars appear to be the same age. Consider the following possible interpretations that could be made from your observations. So we'll go through them, and how many of the 5 choices are possible? Which ones? Explain your reasoning. All right. So I have 2 stars, same mass, and they appear to be the same age. Both stars are the same age and the same distance from you. That could be true. So not only do they appear to be the same age, they actually are the same age. And I'm seeing them, since they're the same distance away, there's no difference in light travel time from one star to the next. So both stars are actually the same age, but at different distances from you. That can't work. They would not appear to be the same age to me, because the star that's further from me, I'm going to see it when it looked younger. It's further in the past. The stars are actually different ages, but at the same distance from you. That could not make them appear to be the same age. If they're the same distance away from me, this look back time is the same for both of them. So they couldn't actually have different ages. If they actually had different ages, but were at the same distance, I wouldn't see them appear to be the same age. All right. The star that is closer to you is actually the older of the two stars. So could that work? Think about that for a second. The star that is closer to you is actually the older of the two stars. And that is not going to be able to work out. The star that is closer to me is going to have the smaller look back time, and so I'm not going to be able to see that as the same age. All right, and the star that is further from you is actually the older of the two stars, and this could be true. So the star that is further from me, so has a greater look back time, I am seeing it further in the past, so saying it's actually older, I'm seeing it at a younger stage, so it appears to be the same age as a star that is actually closer. So the older one could be further and look to be the same age as one that is closer.